Hello everyone. So for our final project is Tradeflow, and it's a distributed system we've built that routes order and figure out how much money each delay or latency actually costs. And the idea is pretty straightforward. In trading, when your order is slow or the market price moves, that gap between the price you wanted and the price you got is called slippage. And every system out there tells you latency went up, but nobody tells you exactly how much that latency cost. And this is exactly what Tradeflow does. So let me just give you some overview about our architecture. It has four microservices. Firstly, there is gateway, the exchange simulator, the dollar cost engine, and then there is router and circuit breaker, which was created by Navneet. And everything talks through SQS queue on AWS. So, firstly, let me just show you how our order structure is created. So, this is our gateway, and fixed message comes in as a raw string with a pipes separated tag. For example, there is tag 38 for quantity, 44 for prices, and 54 for side, like it could be buy or sell. And the parser splits on the pipe and read each tag and build the order structure you see here. So it also stamps a millisecond timestamp. The reason we added is so that we can measure how long the order takes to travel through the system. Let me show you one of the working example. So as you can see, there is um, the price as 150.25 cents, and then there is a quantity of buy and the status is queued. So from here it goes to SQS and the router picks it up. And now the interesting part. This is where the money part happens. The cost engine. It takes each order and runs this exact formula, which is price times 0.00 drift per millisecond times the latency times the quantity. So, for example, if an order sat in the pipeline for like 34 milliseconds, for 5,000 shares order, for example, $150, the estimated slippage would be around just $2.55. But let's just assume there was a spike, which usually happens in pre-market for like 3,400 milliseconds. The same order would cost you almost $255. So, so every 15 seconds, the engine checks the rolling window. So if slipping crosses $500 per minute, it sends an alert to the cost alert SQS queue. And that alert goes straight to the circuit breaker. And this is what Navneet has built. And I will let him take over from here.
Okay. So I build the order router, which is a pretty simple idea. So when the order comes off SQS, the router looks at the quantity. If it is more than 1000 shares, it goes to the priority queue. Everything else goes to the standard. The reason is financial, and for a delayed 5000 share, the order costs way more than a delayed 100 share or order. So they should not wait in the same lane. Now going to the circuit breaker. So this is the circuit breaker configuration. It uses Sony's Go Breaker library. The standard behavior is it opens after 5 consecutive failures and stays open for 30 seconds. But now this is not the interesting part. Let me show you the interesting part. So in this function runs in the background and pulls the cost alert queue. When the dollar cost engine detects that slippage is too high, it sends an alert. So this function picks it up, sets cost strip to true, and for the next 30 seconds, the router rejects all the large order. So it is not just stripping because something error out. It is tripping because the system is losing money. And let me show you one more thing. So here, before the market opens at 9:30, the system automatically lowers the priority threshold from 1000 to 500. So more orders get routed to the priority lane before the daily spike is. It checks the clock every 10 seconds and activates 5 minutes before the open. So we ran 4 experiments, and the we can see the results here. So I'll just talk about the 500 user spike. So here it shows the we have got approximately 25,000 requests with zero failures. But when we look at the response time, we see that the median has 3,400 milliseconds and P99 shows 7,400 milliseconds. The system handled everything, but it was completely saturated. So now let me show you the CloudWatch dashboard. So this is the CloudWatch dashboard. The dollar cost per minute spiked 227 million during the spike test, and that is aggregated slippage across every order in that window. And the routing order reads 9000 per minute because the breaker was actively rejecting the order to the bleeding. Now, Supriya will take over with the conclusion section so that it will be better, I guess.
Yeah.
Yeah. Uh, so now the conclusion part will be taken over by Supriya.
Yeah, so to wrap it up, here is what we took away from this project. First, latency does not go up in straight line. When we went from 10 users to 100, latency got 12 times worse, not 10 times. Past a certain point, every new user make things worse for everyone else. Second, and this was one of the big thing for us, dollar cost is just a better way to talk about performance. You can tell someone that percentile 99 is just 7 seconds and they will just nod. But when you say that spike costs almost 227 million in estimated slippage, that is a completely different conversation. And that is the number that gets infrastructure budget approved. And lastly, the circuit breaker did its job, but it fired late. By the time it kicked in, a lot of orders had already gone through with high latency. So, the takeaway for us is that reacting to a load is not enough. You need to scale before the load shows up, especially for something like market open, where you know exactly when the spike is coming. So, if we had more time, we want to test that directly, run the same spike twice, once cold and once with extra capacity already running, and see how much money the pre-scaling actually saves. And this project is open source. The code, the Terraform, the configuration, the scripts, and everything is available in our GitHub. So if you want to try it out or build on top of it, it's all there. And thank you so much for watching this.